The slide changer was there yesterday. Here it is. Okay, you were able to open. So these are all related to whatever we did yesterday. Nothing related to today one. So just as a recap, while you are using, as a recap, yesterday we sort of built gradient descent from first principles, explaining basic ideas like gradients and how does gradient descent work, right? So that is the basic part of optimization. And today we will move to stochastic gradient descent, right? And how it is different. Now, some people did approach me, and there was this distinction between gradient descent and stochastic gradient descent was not clear to some. So I hope it will become clear today. Unfortunately, there is some let's say abuse of terminology online. So online sometimes people refer to stochastic gradient descent as just gradient descent. So that causes that confusion, but I hope it will be clear today. Okay, so should I go ahead? You are able to access the worksheet? Hmm. Oh, some delays there. Okay. So let us recall our setting, the standard machine learning setting, which is the empirical risk minimization, where we are given several training pairs, right? Let's say AI, BI. I have put AI in bold, so assuming that AI can be some vector or some structure other than a scalar, and BI can be label, which is usually scalar. Then the predicted labels are denoted as Hx of AI, right? So X being the parameters or weights, and AI being the feature from the specific data point, right? So if there is an image, you code it into AI, or whatever, can be text, whatever. And the training loss can be any kind of loss. So then the ERM framework is that we minimize 1 over m, summation from 1 to n. So this is the empirical part, the summation part, the averaging, and then the loss, which measures the loss between Hx of AI, which is what the predicted label is, and the actual label yi. We are talking about training data, so we know the actual labels, right? And our goal is to minimize this. And once we have minimized it, we say that we have learned the model, right? That is what learning the model or training the model means. So then the model will be used, it can be used for prediction, right? And as you remember, this was the expectation. This was supposed to be proxy for expectation, right? Okay. So keeping this in mind, just you know, reinforcing the terminology and notation. N was the dimension, right? Sometimes also denoted by D, but here I'm denoting it by N. N is the problem dimension. So X has N entries. Sometimes this X may not be vector, sometimes it may be matrix also, tensor also. Whatever X is, it has N different values. And then M is the number of data points. So this is referred to as the size of the data set. This is the number of data points. So if there are, 1,000 images, then M would be 1,000. And Hx of AI is the one that is calculating the predicted uh, predicted label. So that can be any model. Example is convolutional neural network or any kind of neural, whatever. That can be your model. right? So neural network parameters are, listed in X. So if there are multiple matrices, whatever, you just list them in X. Right? So X will be our optimization variable because the parameters is what you want to determine. Right? And then we would basically what we will do, or what happens in, for example, neural network in particular, is that this gradient with respect to X, right? The gradient with respect to X, you remember the definition, which is the derivative with respect to each individual xi of the final predicted label. That quantity is calculated via back propagation. Right? So that is a whole thing. I'll not go into it in detail, but essentially it's a way of calculating the gradient. Just a, you could think of it as a program or a routine to calculate the gradient. So what would happen if we use, first of all, what would happen if we use gradient descent on it? Right. So let's, for simplicity, let us denote fi of x as this quantity. The reason I'm denoting it like this is because x is, after all, my optimization variable. So I'll just put fi of x and hide everything else. ai, yi, I have hidden because they are part of the data, so they are just included in the I, the subscript I that is being used. Okay. And then the gradient descent updates are of the form xt plus 1 equal to xt minus eta by m into summation fi gradient fi xt. Right. So suppose that you can calculate the gradient through some means, then this is how gradient descent would work like. Right. I hope this is clear because this is exactly the update that we saw yesterday. Now, so we did not look at this, but I think I should skip this part. But come to the, just ignore this part. We'll cover this later. So what is the complexity of every iteration? If I run gradient descent like this, what is the complexity of every iteration? So you can see that you need to calculate the gradient, which will take at least order n, right? It could take more, but at least order n it would take because each entry has to be ultimately calculated. So order n. Does everyone know of this term, flops, floating point operations? You could say addition, subtraction, multiplication, division, floating point operations. So for every I, for every term here, you will need this many flops. And then there are m such quantities, right? So at every iteration, m times n floating point operations are needed. So this is order mn flops per iteration. Now this is what I use to motivate stochastic gradient descent. So I am saying that this is too large when m is large. N you cannot do anything, you have to calculate the gradient, but m is something that I want to remove from here. So I'm saying that if m is very large, let's say you have 1 million images, calculating or doing this calculation at every iteration where m times n, right, this many flops at every iteration is too costly. So I want to reduce that. I want to remove m from here. And, if you ignore all these, so this mn, I want to remove and get to n, right? So gradient descent is, I would say, not viable if m is very large, right? What if the data set is large? So these are some examples of data sets which, so I mean, this is a nice figure which shows the years and the data set sizes. Now observe here that the data set sizes are in the log scale, right? 10 to the power something, and years are in linear scale. So as the time goes on, the data set sizes are getting bigger and bigger. Even, like, I'm not talking about very large data sets, even normally whatever you get nowadays, it's extremely large. Not possible to, run gradient descent at all. Even like toy data sets, whatever is considered toy data sets, those are also very large, right? So if data set is large, I don't want to have m times n flops per iteration, because ultimately then I'll take, if 10,000 iterations also I take, then 10,000 times that many would be the flop requirement. So I want to reduce that, right? So this is the motivation for gradient descent, right? So what is the idea? So in gradient descent, what we do is we pick, this is one version, we pick a data point randomly, right? So instead of AI, BI, now I have just look at the subscript. It is AIT. IT is a random index out of 1 to m. So I pick a random data point and calculate my gradient at that data point, right? Only one data point. This is not the gradient of the objective function. This is just gradient of the one of the terms of the objective function, right? And then I update this, right? So the m completely goes away here. There is no m here. So this is the stochastic, this is said to be or referred to as stochastic gradient. And as I said, it is not the gradient. So this is not the same as the gradient of the objective function. It is also, interestingly, so it is also not a descent direction, right? If you remember yesterday, we said the gradient is the direction in which the function decreases, but this is not that. This is not the direction in which the function is decreasing, right? This is something else, right? So if you run something like this, so this is the basic idea. Something like this would happen. It will go all around the place. Sometimes even in function value may increase. And our goal is that ultimately this will converge to some point. Okay. And that is supposed to be the optimum. So this is why we are trying to use stochastic gradient descent. And for this, I will give you some intuition. So why this could happen. Okay. So the reason this could happen, first of all, one intuition is that that direction that we were talking about, right? If we fix x to something, right? For example, x could be fixed at a particular value, right? That direction is a random quantity because IT was random, right? Because I picked IT from 1 to m randomly, so it was a random quantity. Its expectation is actually equal to the gradient of the full objective function. What is the full objective function? The 1 by m summation part, right? So that is the gradient, and therefore, and this is the descent direction. So in expectation, the stochastic gradient is a descent direction, right? In expectation, it is the descent direction. So this is what is the summary here. So essentially, by proceeding in the direction of one of the terms, gradient of one of the terms, which is randomly selected, we end up going in the descent direction on average or in expectation, right? So on average, this is the direction of steepest descent. Note, however, one caveat that this expectation is not equal. These two are not equal. This was equal, but these are not equal. Why are they not equal? If you look at here, expectation, what are the random quantities? IT is definitely random because it is randomly chosen. What about XT? XT is also random because previous iterations I also randomly chose some data points, right? So XT is also random. So if I take expectation, it would actually be expectation with respect to all the random choices that have been made so far. But on this side, we have a random quantity, right? So This side it is deterministic, it is an expectation, here it is random. So therefore they are not equal. You have to put one more expectation on this side. Then they would be equal. Right? Any questions so far? Okay. If we remember our least squares setting and revisit that example, then let's say that AI transpose X is our linear predictor, and we are matching it with the actual given labels using squared laws. So let me consider one data set, and it's a very interesting, fun data set, a very synthetic one, but it's very useful to demonstrate this idea. So what I've done is I have created these AIs, like my data features, let's say, I've created by taking 3 random values of AI, A1, A2, A3, and then combining them randomly. Right? So these are 3 random vectors, and I've just combined them randomly. But notice that the index I is on W, right? WI1, WI2, WI3. Now, what is the impact? Ith data point is a random combination of A1, A2, A3. Then for every I, so first data point is some random combination, second data point is some random combination, and so on. So all the data, the entire data set is just consists of random linear combinations of originally only 3 vectors. 3 vectors I start with and take their random linear combination. Now, and coefficients are randomly generated. And then what I do is I put yi is equal to ai transpose x star. Some x star is some value. Again, in the code, I'll just randomly take it, some arbitrary value, and add some noise, very, very small amount of noise, normal noise with 0 mean and variance 0.01 square, right? Very small amount of noise. Now, what is happening in this data set? There is, I mean, one thing you can easily observe that there is a lot of redundancy. All the data points are sort of related to few points, right? That is on purpose. On purpose, I have just introduced some redundancy just to demonstrate or make a point. And let's take m is equal to 1000, n equal to 100. So 1000 data points and 100 dimensional. So this is what would happen basically. Right? So what I'm showing is the error versus number of data points processed. In the gradient descent case, first look at the gradient descent case. What will happen is that it will process the whole 1000 data points and take one step, right? And that taking one step will reduce the error, right? So that's why it looks like a staircase, because it is processing 1000 points and then taking one step, and then 1000 points and one step, right? And in this case, it is taking like 10 iterations or something. Right? So 10 iterations, it is able to converge. But when we compare it with SGD, like it's very, very sharp. Let me show you the other figure, because I want to put the x-axis in log scale so that you can see this number of iterations. Right? So this is the reason, and SGD takes 100 iterations. So here it is actually taking only 40 iterations. Right? So in the log scale, this would look something like this. Right? So gradient descent is waiting for 100 or processing the 1000 data points and then taking one step, then again processing 1000 data points, taking one step, and so on. And on the other hand, SGD, as you remember from the updates, it is processing only 1 point and then taking the step, and then 1 point, then taking the step. So as a result, it is basically has very low error, 10 power minus, between 10 power minus 3 and 10 power minus 4 in about 40 iterations. Right? On the other hand, gradient descent has taken much more data points. The iterations is less. The number of iterations in gradient descent only 10. But the data points that need to be accessed is much, much larger, 10 power 4 as opposed to 40. Right? So SGD is better able to utilize or exploit the redundancy that was there in the data set. actually original data set had redundancy, and SGD, by processing one point at a time and then using that information, is better able to utilize or exploit that redundancy. Right? That is the point of this thing. Right? So the intuition behind SGD is that it is better at exploiting redundancy in the data point, in the data. And like in the very extreme scenario, if data is simply repeated, if you just repeat the data points, then gradient descent will access each repeated data point at every iteration. But SGD samples the data points at random, so repeated points do not matter. I mean, SGD will not even see repeated data point because every point is being sampled at random. Right? So for example, if you repeat everything 10 times, then gradient descent will become worse, but SGD performance will remain same. Right? So this is again demonstrating the fact that it is better at exploiting redundancy. And accessing the entire data set at every iteration is therefore essentially inefficient. So that inefficiency is what SGD is doing away with. Right? So I hope the intuition is clear. Right? Just some history that this is not a new algorithm by any means, known since many years. This is said to be the origin of Robbins-Monroe paper in 1951. It was called stochastic approximation method, the name of the paper. But it was interestingly rediscovered many times by different communities and was known under different names in different places. Right? So for example, LMS and perceptron and SVM, I mean, they were all using different kinds of stochastic gradient descent, right? But without perhaps knowing or without properly connecting all these different algorithms together. So the unification happened like later on after 2000, when all the results from different communities were sort of brought together and compared with each other just to get into a framework which everyone can use. And today, as you already know, it is widely used in the training of neural networks. And another version of SGD which is actually used. So this, whatever I presented so far, it's not really used. It's more like a demonstration version of SGD. But then what is actually used is somewhat more complicated versions. So I'll build to those versions. So first complication or first observation that we can do is that we can use mini batches. So what does it mean to use mini batches? Instead of selecting a random data point, you can select a bunch of data points, right? So at every iteration, instead of selecting one data point, you can select k data points, right? So JT is a set of random indices, right? Let's say you select 10 of them and then average over those 10, right? The one extreme of this is gradient descent, which selects k equal to m, right? Select all 10,000 or 1 million, then it becomes gradient descent. The other extreme is the standard SGD, the earlier version where k equal to 1. And the idea here is that we actually select something like 32, 64, something around that. The reason why we do it is for parallelization, right? How can parallelization help in the context of mini batch? So why do we use mini batch? That is the next question. Basically, the idea is that each gradient can be calculated, each gradient in this curly JT can be calculated separately by a different core or a different computer. So different computers calculate their gradients and then all of them merge these things together, right, to calculate, to form the update term. And that's what we have at every iteration. So this way, what is the advantage? Let's say if you have 32, then 32 gradients are calculated in the time it takes to calculate one gradient, right? So you have a 32x saving. But obviously you don't have very large, you don't have 10,000 cores. You only have maybe 32, 128, 256 maximum, right? You have only that many cores. So therefore mini batch uses that many. I mean, that's something that you can tune yourself, this K value, you can tune yourself to get the best performance. Essentially, the mini batch uh, would take fewer iterations in general, right? Because the K, yeah, different data points. Uh, yes, you update XT for all the machines. So maybe a central aggregator aggregates everything and sends back to the machines. No, no, it's actually the default way. So that is the best way. Hmm. Yeah, I'll come to that. Yeah. So slowly I'll build up the complexity because real is actually much more complex, right? So this is the idea of mini batch, right? So 32 gradients are calculated in parallel and they're all added, aggregated, used to update XT, and then XT is again transmitted back to the individual cores or machines. And this can happen distributedly also. Those machines could be kept at different places also. Then there is some communication delay, which will cause some problems, but it can, in theory, it can work. So if I do this plot, right, this is one of the, this code for this plot is given in in the code worksheet that I shared. So please scroll down and check. This is for k equal to 8. I was just checking how much iterations each of them are taking. So we can see that mini batch is taking fewer iterations, almost 40 iterations, and this one is taking almost 80 to 100 iterations. And this will change depending on your machine, depending on the parallelization capability of your machine, it will keep on changing. Yeah, apart from parallelization, there's no other advantage because ultimately, if you have to calculate everything one by one, then the same time will be spent. So we are saving not in, we are not saving in the number of data points processed, right? It is the time we are saving, wall clock time, you call it. So the time is less, number of data points remains pretty much same, not much difference, even theoretically. Okay. Any questions? Right, so this is all about this module. Let's move to one example first before we get into more complications. Hmm. Yeah. Now, average of, so every core will calculate one vector, gradient vector, right? So there are 32 such vectors, right? You just have to average them through some way, right? So somehow you have to average them. Let's say, suppose that they all send those vectors to one computer. That computer can receive all the 32 vectors and average them. For example, that is one way. And then subtract it from, multiplied by eta, subtracted from xt, calculate xt plus 1. Or it can store xt plus 1 and keep on subtracting 1 by k gradient from whichever machine it receives. Once it is done, it will have a new xt plus 1. It will send to all the other machines. Now, this process is sequential. Calculation of gradient, then calculation of xt plus 1, This part is sequential. You cannot start calculating gradient at xt plus 1 before xt plus 1 is calculated. This part is sequential. But the gradient calculation is parallel because xt is available at all the machines at the same time. That was if you do line search. Yeah. Here they are all random. They're all in all directions because of the randomness. Here also we don't do line search. We cannot do line search. Why we cannot do? Because to calculate function is very, very expensive. What does it mean to calculate the loss? You need to average over the whole data set. You cannot do that, right? So here we cannot do line search. So forget line search for SGD. Yes, yes. Every right, right. So what could happen in practice is that the data set is split into some parts, for example, and stored at different computers. And those computers will randomly take one point from their own part of the data set and use it. That could happen, for example. No, no, no. The same point has to be given. Different points, if you give, then it won't work like this. It won't be like this, right? Same point, you have to start with one x0 at every place, update it to x1, then x1 should be same at all the computers, and so on. Directions, the gradients would be different. Yeah. No, no, no. It's not everyone is not working independently and running the algorithm. They are aggregating everything, right? So it's not that everyone is converging to their own. Each has the same, every core has the same xt at every t. Okay. Okay. So some references when we share these slides, you can go through these. Okay, now let's look at an example before we go do advanced stuff. Because it's important to just get a feel of how it actually really does work. I'm giving a neural network example, not going to details of neural network, but sometimes we use this visual representation, but please remember that there is some underlying mathematics behind it. You could think of neural network as consisting of several layers. Each of the layer is applying one very simple mathematical operation, linear affine transformation, and then one nonlinear operation. So each layer is applying one simple mathematical operation, and then you calculate the predicted, let's say, label from the last layer. Right? So if input data goes here and the output data comes out here, and whatever are the weights used, they become your optimization variable. Right? So you need to do forward propagation to calculate the loss at a given input, and you need to do back propagation to calculate the gradient at a given xt or something. Right? So I am going to use one code which is on a different worksheet. So please open this. Right? I'll just show you how to like run simple SGD on MNIST. MNIST is a data set. Done? right? So essentially, what we are doing in practice is that we are not calculating it ourselves. There are existing libraries or open source tools like TensorFlow, which heavily automate the process. So we don't have to worry about actually applying chain rule and then calculating the gradient. Let us consider this example of MNIST. MNIST is a data set consisting of handwritten digits, and they are all labeled. I think some 60,000 examples are there, right? So the step one, so if you start looking at the code that I have provided you, we are loading the libraries now. If we are going to use this particular thing called TensorFlow, right? And you will see this Keras a lot. So this has very nice tools which are, pretty much everything is automated. Just you need to decide what to do. Everything else is just automated. You don't have to write any loop or anything. I mean, you can still write a loop, but everything is already automated if you want to use it. So we just load this data set. So X train, Y train, X test, Y test, and load from the data set. Then, then depending on how you want to use it, we may need to reshape things, put it into a particular dimension, and then normalize it. Now, these are all steps that are specific to this data set. If you use another data set, another thing, then you may need these steps or not, or different steps. So I'm not going through the computer vision aspects of it. Just these are some steps that you need to do before the data set, right? One hot encoding is another. One hot encoding means that when it is 1, you call it 0, 1, 0, 0, 0, and then if it is 2, call it 0, 0, 1, 0, 0, 0, right? So a particular kind of encoding that works with for this case. Again, specific to the data set and application at hand. Then we are going to use this particular specific style for iterating. So what it is doing is that it's going to provide me parts of data, right, which are randomly sampled from the original data set, right? Let's say 20 points from the data randomly from the original data set. I actually don't have to, sorry, I don't have to actually do random sampling. All that is already implemented. I just have to say that I want to sample like this, right? So here you see from tensor slices, from tensor slices. So this is the part which is setting it up, and shuffle, basically it's shuffling at every iteration, getting some data sets and then shuffling the data set. That amounts to random sampling only. Yeah, mini batch also I have set here some value, and we will repeat over the data set again and again. So basically we'll sample parts of the data set, then repeat. Then the neural network in TensorFlow, that is created like this. Right, this is a very simple neural network, few layers. For every layer, I'm just specifying, for example, I've just said sequential and then adding one layer. And one layer by one layer, I'm just adding. And these are just names of the layers and the parameters. What is the size of the layer and name? Okay. Yeah, of course, if you are more interested, you need to go into more detail. But here I'm just showing that, all this is done in an automated way. And this is the overall loop for SVD. Right. So what is it doing? Basically, with tf.gradient tape. So this is one basically calculation on the forward side. It's able to calculate the scores and losses. And grads will be given by this. So this is doing the back propagation step, calculating the gradient for you. And this is the whole loop, right? For W grad in this trainable variables grad. So this is the whole loop. W dot assign sub means W equal to W minus, and then eta into gradient, right? So that grad is the average of the gradient that it is returning, right? And eta is the step size, right? If you have never not you don't know TensorFlow, you might feel that this is completely different from, it looks completely different from your regular Python coding. It's just that each and every step in TensorFlow is already implemented in a way that it is works best for, it's actually built for GPUs to work with GPUs. So it's implemented in a way that you don't actually implement it wrongly. So they have implemented it. You can also write it as W equal to W minus, but that will generally not work as well as this is working. So some, whatever optimization had to be done on the code side, they have already done it. Okay. And then, some metrics are there, for example, loss, accuracy, those are being selected. And yeah, here loss is being calculated, then updated, because some loss value is being calculated and updated. And things are recorded at every few iterations. You cannot remember that in SGD, you cannot calculate the loss at every iteration. Why you cannot calculate? Because calculating loss itself will require you to access the whole data set. So that is not very efficient. I mean, just to calculate the loss. So you basically calculate it once in a while. Right? And this is finally the learning rate schedule. So what is happening here? Eta, I am just decreasing by a factor of 0.9 after every few iterations. Every bunch of iterations, I am decreasing eta by a factor of 0.9. So eta keeps on decreasing in this case. Okay. So sample result would look something like this. How is it looking? Iterations, test loss, test accuracy. Right. So if you remember, there was a separate training set and test set. So test set is where I'm calculating my accuracy. Right. So this is just to demonstrate a typical workflow. Real workflow would be slightly more complicated actually, but example workflow is this. Right. So if you want to use SGD for your machine learning, these are pretty much the steps you will use. Right. So please, this other examples also you can try out. And without using TensorFlow, also one example is there. Right. So all these are, good things to experiment, and then you can try different things on your own. So any questions so far? That code that I have given, when you connect to Colab, you select GPU runtime. Otherwise, it will take a huge amount of time. Select a GPU runtime and then run it. It should be, you should be able to run it in few minutes, I think. Right, right, right. Loss and accuracy are two metrics, you could say, two different ones. For training, loss is used. Yeah, training. Okay, any questions? Okay, then let's look at some more complexities that do exist in realistic implementations. This one that we just now implemented, it's not used in practice, but we do some variations. One variation you have already seen, which is mini batch. So mini batch is almost always used, especially with GPU availability. Another point is that shuffling and batching. So this is another thing that is actually used We don't, in practice, what we don't do is we don't select a random point and then calculate gradient there. What we actually do is something like this. You have the full data set, you divide it into batches and use batch one at iteration one, right? So I divide it into small batches and use that one at first iteration, another batch at another iteration, and so on till iteration k. And this is called an epoch, right? And then once I'm done with all of this, then I actually shuffle the whole data, and then start again with using batch one, batch two, and so on. Okay. So that's how actually it is implemented. So it's not really randomly sampling arbitrarily. It's more like sampling, what is it called? Without replacement. Or sampling and then another batch, another batch, another batch. Amounts to sampling without replacement. Then another point is learning rate schedule. Just preview of that we saw. Learning rate star equal to 0.9. Learning rate was decreasing by 0.9. But there are all sorts of different learning rate schedules used in practice. These are different ways you could have. Inevitably, learning rate is always decreasing, but how it is decreasing, that different, let's say different domains have different thumb rules to use. So for example, if you talk about computer vision, they will say that you should decrease learning rate like this. But if you use for something else, they'll suggest or advertise some other schedule. So many learning rate schedules exist. Right. So depending on epochs, for example, or depending on the iteration itself, this is less common, depending on the iteration. Depending on the epochs is very common. So for some epochs, you run with some rate, then as epochs go ahead, keep on reducing it. Right? Remember, epoch was one pass through the whole data. And typical, you will take several passes, 100, 200 passes in a typical setting. Then there is also wide usage of adaptive learning rates. So this brings us to a whole class of other algorithms which are variants of SGD built upon SGD, like AdaGrad. So what is AdaGrad? If GT is this, GT is the gradient, and its jth entry is denoted by this, then in AdaGrad, the update is something like this, right? So it is not eta t times GT. It is actually, so jth entry, if we talk about jth entry is having this in the denominator, right? What is the impact of this term in the denominator? So it's very interesting. Let's say ignore epsilon. What is happening is that as t grows, right, these GTs contribute more and more, right? Because this is actually GTJ square, some scalar value square. So this increases as t goes on, right? So this increases, and that causes a decrease in the overall eta. You could think of it like this: eta divided by this thing goes to become smaller and smaller. So that's what the idea of AdaGrad is. Essentially, it is adapting the step size to the actual value of the gradient. Right? And the idea or intuition is that, let's say, for some j, all the gradients could be large, and for some j, all the gradients could be small, and therefore you can use different step sizes for different j's. J's means dimensions. Right? So that is the idea. It is really not difficult to implement in practice. You could maintain some VT for this, and at each iteration update like this: VT is equal to VT minus 1 plus GT. This is for Hadamard product. In Python, you just directly star you can use. So it will just multiply each of the entry of GT. Right? This is entry-wise product. And eta j can be set to this eta divided by square root of epsilon plus VTJ. Right? So very simple to implement. Uh, it uses accumulated gradient magnitude, and the code would look something like this. So ACC grad plus equal to grad square, right? This will take you the square, and then you will accumulate here, and then accumulated one you will take square root, right? And you can start with ACC grad equal to epsilon, so that the epsilon term will also be there. Okay, so this is ADA grad. So this is a small variation, as you can see in terms of code. It's a small variation, but it is seen to accelerate in some scenarios. Tuning, it reduces the tuning that you need with this step size, right? And sometimes, however, the problem could be that accumulated gradient could become too large. What happens if accumulated gradient is too large? Yeah. Yeah. So this gradient contribution is less and less, and that could be detrimental. So if initially it is too large, initial gradients are too large, then you have too much accumulated, and then your whole rate slows down in that direction. So this could be due to bad initialization. So other techniques are also there. For example, RMS prop called root mean square propagation, right? Avoids the gradient accumulation issue. So it is slightly different in the sense that instead of accumulating it like this, we are using what? What is this? Moving average window, right? It takes moving or running average using a factor of rho, right? What is it called? Exponential, exponentially weighted moving average. And then we are doing the similar kind of thing, but VT is collected in a different way. Instead of accumulating, you actually take a exponentially weighted moving average. So this sort of forgets the past. If you really have a bad initialization, then this will forget it, provided that rho is not very close to 1, right? And so this is how this would look like, and you can accumulate it and see that the impact of G0 J becomes less and less as T goes on. So here basically this is just showing that the gradient magnitudes, how they are decaying with no, sorry, this is showing the step size. The left side is showing the step size versus iteration for ADA grad and RMS prop. So in RMS prop, you can see that the step size is also increasing sometimes. It was decreasing here, then it increases. But in ADA grad, it was the usual decrease, right? And on the y-axis on the right, I'm showing the gradient magnitudes. Right? So as gradient magnitudes become smaller, the step sizes are increasing in RMS prop. Okay. Then another popular one is Adam. Adam has two changes, exponentially weighted for both gradient and its square, and bias correction of RMS prop. So you maintain, instead of only maintaining VT, I'm also maintaining MT. MT is the exponentially weighted moving average of the gradient itself, right? So gradient and its square. And then bias correction is like if you take expected value of this, it turns out that this is not equal to the expected value of the gradient. So if for example, if you take this to be sigma square, then it will be sigma square times 1 minus rho raised to the power t. And therefore, what Adam does is, right, this bias that is there, what Adam does is that it divides it by 1 minus rho raised to the power t. So that is like some way of correcting that bias. So Adam updates would look something like this. Now they look very different from SGD, but really they are built from SGD. All the intuition is coming from SGD, just that there are some things to try to correct it. So if we summarize the adaptive step sizes, these are also called momentum methods, by the way. Uh, all different names are there, all sorts of names are there. But if you encounter momentum methods, then they are mostly talking about this in the context of SGD. There were lots of different algorithms in this duration. And now pretty much few algorithms are standardized. Always those few algorithms are used. Perhaps I could say Adam is perhaps widely used. So we'll come to the complexity later. All these methods are already implemented in this Keras or TensorFlow that I was showing. Already, implemented. So you can implement them yourselves, like I was doing w.assign sub, but you could also call one of these routines to implement a method. But then it is somewhat, you need to get the intermediate iteration information from that library. Right. Then one more thing that is also used is regularization, which is, so this is more of a machine learning concept, that you add one lambda x here. So there's like x L2 norm square or L1 norm. And if the regularizers are differentiable, then SGD variants will work as usual. And if they are non-differentiable, then some other variants exist, like proximal or different types of variants are there. So this is also like widely used. So if you see it, don't get confused. It's a very common thing to do. Okay, so this is all I wanted to cover about gradient descent and SGD, at least on the practical side. I have not covered some of the things, like I have not covered any constrained optimization, because that is a big area in itself. And it's not that it's not important, it's very important, just that I did not get time to cover it. If there are constraints, you cannot use this classical SGD, you need some variations, you need some modifications to it, like projected SGD to handle. And then they would have higher iteration complexity and higher per iteration flop count, or similar iteration complexity but higher per iteration flop count. And then you also need to, if the constraints are complicated, you also need to know about some Lagrange duality. Training generative adversarial networks is also done in a similar way, but slightly again modifications of classical SGD. And then we did look at hyperparameter search. Even within Adam or within RMS prop, there are lots of different parameters, rho 1, rho 2, eta. And then you need to actually tune your framework or tune your algorithm to actually select the correct eta and correct rho 1, rho 2. So that is also part of your process. So when you actually run the first time, it may not work as well. And then you may tune it. Sometimes people who have already run, they may suggest to you that, okay, try using this value, it works better for this kind of examples. Those are all example specific or area specific, right? So for example, even the paper itself, the Adam paper itself says that, no, you should use this value. It's for the examples that they have tried. For those values, some values, those have worked well. But it's not universal by any means. Nothing here is universal. Even Adam itself will not universally work better than SGD everywhere. It works better than SGD for some applications, while for others, SGD works better than Adam. So it's very domain specific. After this, it becomes very, very domain specific. If you have a single parameter, you can do a very simple line search, but few parameters, you may need to do grid search. There is another type of optimization which is commonly also used, which is Bayesian optimization. So Bayesian optimization is again other like black box optimization technique, which can find these hyperparameters by running the algorithm many, many times. Let's say 20, 30 times you can run, and it will give you the parameters that work best. But then you need to run 20, 30 times. So if each run takes 10 minutes, then 20, 30 runs take 200, 300 minutes. Okay. So what I have done so far is I've covered simple algorithms and deterministic functions. I've not covered Newton method, but gradient descent. And I have not covered constrained optimization, too much of hyperparameter search like Bayesian optimization or analysis so far. Now, I would say that all this research started or became very common after 2012. But at this point, most of these algorithms are fairly mature. They're widely used, and there are, depending on the application, as I said, there is standard settings in which you should use them because they sort of work always. Uh, once you are done with this tutorial, you should basically keep that MNIST example that I gave you, that you should keep close. And whenever you get a chance, try to modify things there. Right? There are a lot of different steps are there. Just try to modify, try to see what will happen. What will happen if you change the learning rate, or what will happen if you implement Adam on it, or what will happen if you pick like RMS prop, something, all the different variations you should try. There is also a related data set which is called MNIST fashion. You can try that. Just very, very similar, not much you have to change. You can use the same neural network, and you can use also I would say check out the built-in optimizers. So you implement SGD, and then you check out the built-in SGD implementation and see whether there is difference. Sometimes built-in optimizer will beat your implemented one because they use certain parameters which work well for MNIST, for example. Right? So that is definitely possible. And keep experimenting till you understand every line. There are other TensorFlow Keras example. All these are given, by the way, on the website of TensorFlow. You visit the website of TensorFlow, they have lots of different examples. You can, as I said yesterday, you should use ChatGPT to understand this code. Something is not clear, you can use ChatGPT to understand what exactly that step is doing, and ask it, if I want to change it, what should I modify? Right? That's a good way to learn this area. Some references. So now we'll discuss some analysis, like I have maybe half an hour or so. I'll discuss analysis, but before that, any questions you have? So with this, I think all of you should be ready to implement SGD for whichever application you can think of. From simple to complex, like simple is just write it in Python. Don't worry about GPU. Complex is more like TensorFlow. Worry about GPU, make everything so that it works in parallel. So for simple to complex, you should be able to implement any of these variations. Any questions? Okay. So then let's go to the sum analysis. Sum analysis, just you know, uh, just to get an idea of these things, how they are analyzed in theory, and what kind of standard results exist which have analyzed it, and I'm not going into too much into the current research, more like, whatever is already well known now. So one thing that you can ask, or we often ask is, there are so many algorithms. Let's say I said 2012 to 2017, there were so many algorithms proposed. So how do they compare themselves? And as we were discussing, it's very domain specific. So that's not a good comparison. Suppose I say that for MNIST, this algorithm is best, and then for MNIST fashion, another algorithm is best. That is not a good way, right? Because then it is just difficult. It becomes unwieldy because data sets are changing every day. So what is a better algorithm overall? That is a more interesting question, right? Uh, Generally, the answer depends on a lot of things. It's not a simple answer. So it depends on the implementation. It depends on the language that is used, the libraries that are available. So for example, when you go to TensorFlow, everything is, properly implemented, optimized. So obviously, any algorithm you implement there will run fast. There's no doubt about it. But even once you keep all those things constant, then which is the better, right? You could think of it like that. So is there a system independent metric? Another question arises. So for example, if there a metric that we can use which is independent of implementation language used and libraries, right? So what would be that metric? So that is the Oracle complexity metric. So what is the idea? That, Oracle complexity is something like this. So there is a there is an oracle to which I give X and it calculates Fx, right? And then I can just count the number of calls that I need to make this oracle. Oracle is, I want to minimize the number of calls that I make to this oracle. So now what I have done is uh, abstracted away all the dependence on the implementation. So whatever was the implementation dependence, like your code was faster or whatever, that is all abstracted away, and this is just becomes a black box. Right? So this is one metric that we will use. Now we were discussing random search yesterday, right? Did anyone think of what is the complexity of random search, or what is the number of iterations required by random search? Did you think of that example? Let's say in 1D, let's start with 1D. In 1D, let's say you have the interval 0 to 1, and your optimum is somewhere, and you do random search. So how many samples would it take for you to find a sample which is epsilon close to the actual optimum? That is the question. We have increased the board, right? So just a little bit. Sorry, 0 to 1. Right. So what I've done, what I've drawn is interval 0 to 1, and there is some interval around x star which is of size epsilon on each side, so 2 epsilon. Right. And if I were to do random sampling, what is the probability that I'll end up here? 2 epsilon only, because just, we are choosing uniformly at random. So 2 epsilon is the probability that I end up here. So this is what, so how many samples do I need to ensure that I do end up here? 1 by 2 epsilon, right? So in this context, the Oracle complexity, right, is what? 1 by 2 epsilon. This is the number of iterations of the random search that I need to ensure that the optimum that I report finally is epsilon close to the x star on average, right? In expectation, this is the number of iterations, right? Because it's a random, so of course it could be different than 1 by 2 epsilon, but average is 1 by 2 epsilon. Okay. So this is in 1D. What about 2D? In 2D, let's say I take a box around the optimum, right? Box around the optimum, let's say of size 2 epsilon in each. So the oracle complexity will be, right? So here is the curse of dimensionality. As I increase n, random search is very efficient in this. 1 by epsilon it is taking, right? Not very efficient, like it's okay, it's reasonably efficient. But as I increase n, random search complexity becomes 1 by epsilon raised to the power n, right? So if for example, epsilon is 0.001, 10 power minus 3, then the random search oracle complexity will become 10 raised to the power 3n. You can't use it beyond 3, 4, I don't know. So that is all about random search. So similarly, actually, we want to calculate oracle complexity for all algorithms. So wherever algorithms are there and we can calculate the oracle complexity, we know how much time they are going to take in theory. Now, this is, by the way, this is the in expectation, but it is also worst case scenario. Best case scenario is what? You just do it once and you land up here, right? So, but you don't know what is x star, so you will run a certain number of times anyway. So, but no matter what happens, no matter where x star is, you will always need this many number of iterations, right? On average. So it is independent of the actual problem, right? So we want to have bounds which do not depend on the actual problem like computer vision or LLM or whatever. Should be independent, mostly independent. Should depend on classes of problems. So one thing that we'll use here, it is Lipschitz continuity. So Lipschitz continuity function is said to be G Lipschitz if fx minus fy absolute value is less than equal to G times norm of x minus y. So this is Lipschitz continuity definition, right? So this is a class of functions. G Lipschitz continuous functions is a class of functions. So this is the kind of class that we are looking at. Equivalently, it is equivalent to say that gradient norm is bounded by G. In other words, the growth or the decrease rate is bounded by G. This is how fast or how it can increase or decrease at any time, at any point. And if this is G is not too large, then essentially you cannot have any sudden jumps. So Lipschitz continuous functions are those which do not have such sudden jumps. And then smooth functions are those whose gradient is Lipschitz. So the gradient does not have sudden jumps, right? So the definition is like this: gradient fx minus gradient fy norm less than equal to L times norm of x minus y. Equivalently, the second derivative or a Hessian norm is, which is the largest eigenvalue of the Hessian. Hessian is a matrix, right? For a vector, the Hessian is a matrix. So the Hessian matrix has second largest eigenvalue less than equal to L. Right? So the maximum growth or decrease rate of gradient is bounded. So this is the class of functions that we can look at. This is one possible class. There you could similarly think of other classes. But this is one possible class for which we can look at. So let me show you the analysis for this class, just to give you an idea. So let's start with quadratic function. Very simple to consider. Half x transpose qx. Q is some matrix. Gradient is what? Q times x, right? This is vector gradient, remember, vector calculus. So Q times x is the gradient. And if you calculate the difference between gradients, then it will come out to be Q times x minus y norm square, which can be written like this, right? X minus y transpose Q square x minus y. And if you remember, there is one bound called Rayleigh quotient, comes up in linear algebra. If you remember that bound, you can bound it like this. Essentially, this is bounded by lambda max of Q square. Lambda max is the largest eigenvalue of Q. So the L smooth condition, L is equal to largest eigenvalue of Q. L is equal to largest eigenvalue of Q. This smoothness, what it implies, smoothness, if you remember, is that gradient does not change very quickly. What does it imply about the original function? The function also does not change very quickly. In fact, because the gradient does not change quickly, the function is upper and lower bounded by a quadratic function, right? L smooth function satisfies the quadratic upper bound. So this is the kind of upper bound. Fy is less than equal to fx plus gradient of fx transpose y minus x, right? Looks very much like Taylor series, right? But the last term is different. Last term is a upper bounding term, L by 2 norm of y minus x square, right? So this is, so for example, at this point, there is an upper bound. At this point, there is an upper bound. So at every point, there is an upper bound, and that upper bound, like the point at which the upper bound is there and its slope depends on x and y, right? But its curvature L is fixed. So there is also similarly a lower bound, right? So f is L smooth, then minus f is also L smooth, because you can replace in the definition, you can replace f with minus f. Minus f is also L smooth, so therefore you will get this kind of bound. And this is the quadratic lower bound. So I'll show you a nice animation. So smooth functions are upper and lower bounded by quadratic functions. Right, this is a nice animation. So essentially, I am calculating the red one, which is the upper bound, and the green one, which is the lower bound for this function at every point. Right, this function is 1 by 1 plus x plus minus y. Right. No, they are not constant. They are changing because they are touching this function at different points. Right. So they are not constants. Right. Observe very carefully. The green curve is changing, and the red also. Its curvature is constant in the sense that L value is constant. Everything else is changing. It's moving, and its tangent is also changing. No, no, no. Its tangent is also changing. As I said, only its curvature is constant, which is how curved it is. That part is constant. Everything else keeps on changing. Okay, it's not displacing. You displace, this won't work. Right. So this is the upper and lower bound. Now, why did I introduce this? Because you can imagine that this class of functions which is smooth, which has this upper and lower bound, you can then bound. You can create bounds on how fast, let's say, gradient descent or stochastic gradient descent will work on these kind of functions. So this is one way of creating this kind of bounds, right? By assuming smoothness. Not to say that smoothness is always true, but more like for smooth functions, this is true. If it is a non-smooth, then do something else. So, so let's look at this gradient descent. Note that there is no x star. We can't compare fxt with fx star here. So we can't say that I clump epsilon close to x star. That metric I cannot use because the gradient descent may never get close to x star. It may only go to local minimum. So I need a metric which measures how far I am from the local minimum. How do I measure that? What is true at the local minimum? Gradient is 0. So I can measure the size of the gradient. If the norm of the gradient is large, it means I'm far from the local minimum. If it is small or 0, then I am at the local minimum. Right? So this is the metric that I will use. And gradient descent converges to stationary point. So therefore, this is what we want. And the updates are like this. Now let us analyze. So I'll write down 3 equations. I'll number them for you to remember. First one is I've subtracted x star from both sides and taken norm square. Right, maybe that was not needed. Anyway, so this is the quadratic upper bound that we had. And I can substitute in place of y. So the quadratic upper bound we already derived. It was true for all xy. I substitute in place of y xt plus 1 and in place of x xt. Right? And y minus x obviously will become minus eta times gradient because this was the update step. So once you do this, you get this kind of equation. Right? If you assume that this eta L by 2 is less than 1, right, then you get this kind of equation. Right? Now this is only one step. Forget the previous slide. So this is only one step. If I ever apply gradient descent on a smooth function, by the property of upper bound, by the property of smoothness itself, what do I get? What does this equation imply? It implies that the function value going from xt to xt plus 1 always decreases, and the amount it decreases depends on the norm square of the gradient there. Right? So this is a very nice inequality. So maximum function value will be upper bounded by this. So at least this much it will decrease. It could decrease more, but at least this much it could decrease. Okay, so this is the decrement property of gradient descent. The function decreases monotonically, provided that eta is small enough. Now here is, we are saying in theory, whatever we saw in practice, that eta should not be too large. Now we are seeing this in theory. Then if I rearrange and take telescopic sum, so this is another trick that is used in this context, which is that I have just rearranged it, eta norm square less than equal to 2 fx1 minus 2 fx2, and then written down this equation from 1 to t. And what I'll do is I'll add them up. So when I add, what will happen? These terms will cancel. Right? When I add, what will happen is that many of these terms will cancel and I'll be left with this. Right? So we have eta times the total cumulative gradient from x1 to xt less than equal to 2 fx1 minus 2 fxt plus 1. And you can upper bound like this because, why you can upper bound? Because fx star is ultimately the smallest f for any x. So fxt plus 1 is greater than equal to fx star. So minus fxt plus 1 is less than equal to minus fx star. Right? And then, so this is what we have used. Then suppose we initialize such that the original initial value is within b distance of the optimum. Right? If we initialize like this, BF can be anything. I mean, BF can be large also, as long as you know that there is a BF. If we initialize like this, and we use the fact that average is greater than the minimum, we can say that the minimum gradient from 1 to t, minimum gradient norm square from 1 to t is less than equal to this average, which is less than equal to 2bf by eta t. Right. So this is my simple result. Only property I have used is smoothness, and the fact that it is initialized not too far, and the fact that eta is not too large. Right? Those are the three things I've used. And I'm saying that the minimum value of the gradient from 1 to t, wherever it is minimum, let's say it could be larger in between or smaller in between, but wherever it is the minimum, I'm guaranteeing that that minimum value is decreasing, right, with t as 1 over t. So as t becomes 1 over, like t becomes 100 to 1000, that minimum value should decrease by factor of 10, at least. In the worst case, it will decrease by factor of 10, could decrease more. Right? So this is my result, and then I can translate this result. I've taken square root on both sides. So I can translate this result into like oracle complexity, because I could say that I want this minimum to be epsilon. Right? So I'll keep track of all the gradients, and wherever the minimum is, I want that to be epsilon, because I want to be epsilon close to the stationary point using this metric. And therefore, I will say that number of iterations needed is, I've just inverted this or taken inverse. So epsilon, this is equal to epsilon, so therefore t should be equal to 2bfl by epsilon square. So now this kind of equation tells us the oracle complexity in terms of epsilon. Also, it tells us other things about the algorithm. For example, the iteration count will be larger if you start from somewhere which is very far. If bf is larger, then it will be larger. If L is large, right? L is large means the upper and lower bounds are very loose. Then obviously this bound is also very loose. Right? And then it decreases as 1 by epsilon square, similar to what we were getting here, but worse than this. Right? So this is the oracle complexity of gradient descent. Now you could change this assumption of smoothness. You could use more assumptions, less assumptions, different kind of assumptions. All those works are out there. All sorts of things people have done. Okay. Then what about hyperparameter? So this is, sorry, let me just go back. Yeah. So here, what I had done was picked eta equal to 1 by 2L. I forgot to mention that. I picked eta equal to 1 by 2L. Because this was saying that I should pick eta to be as large as possible, so that this is as small as possible, right? And the maximum I was allowed to pick was 1 by 2L or 1 by L, I think. Is it 1 by L? 1 by L. So maximum I was allowed to pick was 1 by L. So therefore I picked 1 by L. So in this case, the choice of eta is also coming from here. And this is reflected in practice. In practice also, remember what I said. I said you pick a large value of eta till the point it works. Don't pick a very large value so that it stops working, but you pick a large value of eta till the point it works. And here, theoretically also, I am doing the same thing. I'm picking as large a value of eta as possible till the point it works. Right? That may not always be the case, but in this case, that is the scenario. Okay. Now, when we come to like SGD or ERM formulation, we are seeing that if gradient descent iteration complexity is L by epsilon square, then the gradient descent, if you apply on this problem, then flop count will be Mn into L by epsilon square, and we were wanting to remove M, right? So can we have a flop count that does not depend on M? That is our goal. That was our goal with SGD. So let's first of all modify the Oracle definition, because the same Oracle definition cannot work. We cannot get the gradient of the whole function, the average over the whole data set in one go. That would be too much. So let's say that the Oracle only provides one data point, gradient of one data point at every, for a given I. Right. So with the new definition, gradient descent complexity would be m 1 by epsilon square or log 1 by epsilon some under some other assumptions. So complexity should not depend on m. That's what we are going. So SFO Oracle gives this, right, gradient, stochastic gradient for one data point. And this is called stochastic first order Oracle. And this complexity of gradient descent is ml by epsilon square. And we want a lower Oracle complexity for SGD. Right. So now one thing we need to do a little bit of probability, because in this case, because things are randomly chosen. So SGD update looks like this. And since all these indices were randomly chosen, hence x2, x3, these are also all random. And therefore iterates are random. And therefore, when we take this expectation is with respect to all the random variables so far, I1 to IT, not just with respect to IT. So if I want to take expectation with respect to IT, I should use a different notation. I should say conditioned on I1 to IT minus 1, or I should say expectation with respect to IT. Right. So for that, I'm using the notation ET. So expectation with respect to IT is really easy to calculate, because it is just uniformly distributed from 1 to m. You will just average it, right? So essentially, the full expectation can be seen as a nested expectation from E1 to ET. Right? Expectation with respect to I1, with respect to I2, and so on. Okay, so if you keep this in mind, then what is ET gradient of IT xt? It actually depends, xt only depends on I1 to IT minus 1, and FIT only depends on IT. And therefore, this expectation, xt can be treated as a constant, and therefore this is given by expectation with respect to IT is given by gradient f xt. Okay. And then if you, of course, if you take nested expectations, then full expectation on both sides will come. Similarly, actually, you can use the variance idea also. So similarly, you can calculate variance. So if you want to calculate variance with respect to IT, then it would come out to be like this. You can again take expectation with respect to IT. So xt is fixed, and you can take this expectation. Sometimes what we do is we assume, because this is something that depends on the data, so we assume that it is bounded by sigma square. This is one assumption. The variance of the data is bounded. Variance of the gradients coming from the data is bounded. This is fundamental quantity that depends on the data set and the function that is used, the network and so on. Right? So variance is given by this, ET gradient norm square minus the gradient whole function gradient norm square. And the variance of FIT at xt, so here this is another thing. So if this is less than sigma square, then expectation with respect to IT is less than sigma square plus this quantity, because there is a minus sign here. Okay. So this is what we will use for analysis. Right? This is what we will use for analysis. So if we derive the SGD Oracle complexity, again, don't worry if you don't understand it in the first go. Just 2-3 steps really. We'll assume two things. We'll assume that function is L smooth and the variance is bounded by sigma squared. Just for simplification, we have taken. that under these assumptions, then oracle complexity is actually L by epsilon raised to the power 4. Right? If we count number of iterations, gradient descent is better. But if we have M there, then as long as M is sufficiently large, SGD would be better. So we use the quadratic upper bound, right? In the same way, right? Same thing, almost similar thing we are doing now. But here, instead of gradient, we get gradient of the ITth point. And here, instead of gradient, we get the gradient of the ITth point. Then take expectation with respect to IT, right? So this term will be fine. Here we will use the sigma square bound that we used. So those two bounds that we derived for expectation and variance, we will use them. And this gives this equation. Now it's just a matter of, massaging this equation so that we get the correct term. For example, again, we could use that eta thing, that eta has to be small, not too large. That will simplify. But so here, I think let's observe this for a little bit. Compared to gradient descent, what is the difference? If you remember gradient descent, what is the difference between gradient descent and this one? In gradient descent, this last term was not there, right? So there was a monotonic decrease, but now, because of the randomness of the gradient, there could also be increase. There is decrease because in expectation I'm going in the descent direction, but there could also be increase because of the randomness of the gradient. So the theory is exactly saying what is very intuitive for us. There is randomness, so it could increase, but on average, it will keep on decreasing. Time is up. Okay, thank you. Just I'm left with 2 slides maybe. So then we do the telescopic sum like earlier. Subtract fx star from both sides and write it in this way. And this will give us the average. So if I rearrange, I'll get this thing. So average of the expectation of the gradient norm square less than equal to 2 quantities. One is depending on delta 1. What is delta 1? fx1 minus fx star, same as BF earlier. What is eta L sigma square? A term depending on the variance, the noise in the data, because of which stochastic gradient descent is different from gradient descent. So the noise part and the initialization dependent term, both are there. In this case, however, we should not choose a very large eta because the eta is here also. So I should choose what eta? I can choose an intermediate value of eta. I could choose, for example, the eta that minimizes this bound, not necessarily minimizing the iterations, but the bound. So in that case, I can choose eta to be 1 by square root t or something. I think you can just set these two terms to be equal. So then the whole thing will be minimized. If you minimize eta and plug it here, you will get this many iterations. So if this is the minimum for eta equal to this. So if I use this idea, and also like I need to do some expectation inequalities, then I get the oracle complexity equal to T equal to order delta 1 L sigma square by epsilon raised to the power 4. Right. So this is as opposed to, order M times L by epsilon square, right? So the M is replaced with 1 by epsilon square. So now you can see how large M has to be in theory to beat SGD. How large M has to be, or how large M can be, so that gradient descent is better. If M is less than 1 by epsilon square, gradient descent would be better. M is larger than 1 by epsilon square, this would be better. Right? Very rough way of calculating because you're only comparing bounds. But that is also intuitive. Also, whatever we thought, that is true. If M is not too large, then maybe gradient descent would be better. Of course, also depends on sigma square. Sigma square is very low, then SGD would still be better because sigma square was not appearing in gradient descent. So that's all for analysis and uh, implementation of SGD. I hope you liked the tutorial and you will be able to use this, both the things, analysis and uh, implementation, in wherever you want to apply. So that's all. Thank you. So, yeah, like this. Thank you.